Okay, we're back on the air. So first of all, homework 3, the dumb exercise is due today. And, but we're getting jammed up at the end in part because of the holiday next Tuesday. So what I said is,
it's best if you hand in homework 3 today. Makes it easiest for me. Tomorrow's good too. You can bring it to my office or leave it in my mailbox. And also you could drop it off on Saturday. So I'll come into the office on Saturday afternoon and pick up anything that's there. But if you drop it off in my office, first of all, you have to get into the building. Door may be locked, I don't know. And then you won't be able to get into the office where the mailboxes are. So you'll have to slip it under my door. So make sure you can do that. And also, please put it in an envelope and seal the envelope. Otherwise, they get pretty messy when they go under the door. They catch under the door and they get stuck. So just put it in an envelope like this and seal it. Just put some tape over it or something and slip it under the door. I'll pick it up on Saturday. And if you hand it in later than that, better late than never, but I want to grade these things over the weekend, so try and get them in by Saturday afternoon the latest. So are there any questions about that? How many people have done homework 3? So most of the people who are here. And it worked out, right? Everything worked out the way it's supposed to? Okay. So it's straightforward, actually. You just have to do it. Homework 4 is just a continuation in which there's a change in case number 3. So instead of giving you a constant again, which wouldn't make any sense, I gave you another random variable. And otherwise, except for that piece, which is new, homework 4 is easier than homework 3 because there are no graphs. So I'd like to make that due. It should be due a week from today, because I guess there are no more questions on that, or are there? However, if it's due a week from today, you don't really have any time to ask questions about it because we don't have any class on Tuesday. So I'll make it due a week from Tuesday. Okay? So are there any questions about homework 4? I mean, I went over the whole thing, but you didn't have a chance to think about it in advance. So the one difference is, okay, let me just, see if I can find a copy of the latest version of homework 4. Okay, for homework 4, there was case number 3. And there you're given the density function as being 0 if t is negative, and 2 minus 2t if t lies between 0 and 1, and 0 if t is greater than 1. So if you draw that density function, it looks like this. Here's f, little f, that's the density function. Here's t, here's 0, here's 1, and this would be 1 and that would be 2. And so the graph of this would look like this. 0, and there's discontinuity to 2, and it looks like a triangle, and 0. Now, this is just a slight change from the case where x is uniform 0, 1. Because in that case, the density function is just a box. So, in this case here, this is where x is uniform. Zero, 1. And in that case, the graph would look like this. 0, 1, 1. This area is 1, that area is 1. So I took something that had the same range between 0 and 1, but changed it in the simplest way possible. So instead of making it a box, I made it a triangle. Now, in this case, the distribution function, you know, looks like this. It would be capital F. And remember, capital F is the cumulative area under little f. So if I plot that area, that's t, and that's t, and this is the value 1, then if I imagine that I look at the area as t moves from left to right here, the cumulative area and the graph below it would look like this. So that area increases linearly with this distance. Now in this case, the same kind of thing, except the curve would look a little bit different. So now, capital F being the cumulative area, again here's the value 1, and remember every distribution function, which describes cumulative area, starts at 0 and ends at 1. Here's the value 1. This is 0. That's 1. And now again, it's going to start at 0. It's going to end at 1. But now you can see that as I move from left to right, for any little interval of, any little window, the amount that's enclosed is going to decrease as I move from left to right because the graph is higher here. So that means that what you're going to see is that the area is going to increase fast and then slow. And so the graph should look something like that. Of course, you got to get the formula for this, which you get by integrating, just the way you get the formula for this by integrating that. And then when you generate the random variables, what you do is you're going to add two random variables, two realizations. The first realization is from the uniform. You already know how to do that. And then the second one is from here. So what you have to do is you have to take this density function, you have to change the distribution function, then you have to represent r in terms of x or x in terms of r this way. As usual, that's the inverse transform method. So you have to solve r is equal to capital F of x, and then solve that backwards to get x as a function of r, and then write that in code, and that takes that's just a single instruction, and that will generate this x. So you generate this one, you add them, that's y, and that's the story. Okay? So I don't want to tell you how to do this any more than that, because if I do that, then there's nothing left. Now the other piece is, you've got to calculate the expected value. Remember that y is equal to x1 plus x2. So one of the questions is to calculate the expected value of y, which is the expected value of x1 plus x2. And there's a theorem that says that that's the expected value of x1 plus the expected value of x2. So this is easy. You've already calculated the expected value of x1. To get the expected value of x2, you take the density function, you plug it into the formula for expected value, and you calculate it. That's easy. That gives you this. You just add them up. So it's much easier to use this formula than it is to calculate the density function of y and put that in the formula. So this is a major savings. Now you also want to calculate the variance of y. And of course that's the variance of x1 plus x2. And now if x1 and x2 are independent, which is what we're assuming here, then the variance of the sum is the sum of the variances. So once again, you already know the variance of x1. That's this one right here. You did that earlier. To get the variance of x2, you apply the same argument to the density function here. You get those two, you add them up. Again, this is very easy. And then finally, you want to calculate the probability that y lies between 0.25 and 1.35. Is that right? And so the way to do that, or a way to do that anyhow, is to calculate the integral from 0.25 to 1.35 of the density function of y. In other words, the area under the density function curve between 0.25 and 1.35. So in order to do that, you've got to get the density function of y. And that's the convolution stuff. That's the new big deal. So everything else so far is easy, straightforward. So then what I did in class was I derived the formula for the density function of a sum of independent random variables. And the argument went like this. Now I'm going to do it quickly. But what I did is I found the distribution function of y. The reason I did that, remember, is I'm making a derivation and I want to use physical reasoning. And this is a probability, whereas density function is a probability only when you take areas. The density function itself is not a probability. So this is the probability that the sum is less than or equal to t. So the argument I made is this. I said, well, first of all, what's the probability that one of the variables, say x1, takes a value u? And part of the intuition that you're supposed to be developing in this course is to recognize that if I take the density function, evaluate it at some point, and then multiply that by this differential, even though this is not a number, this represents an operation, the way you interpret this is to say, this is the probability that x1 lies between u and u plus du, or lies in an infinitesimal strip at the point u. So it has no numerical value, but there's going to be an infinite number of these essentially zero infinitesimal things, and then when you add them up, that's what calculus does, you integrate, then you get some non-zero value. Okay, so this represents the probability that one of the random variables equals u, and then I multiply that by the probability that the other one, x2, is less than or equal to t minus u, which is the distribution function evaluated at t minus u, and then I add those up over all possible values of u from minus to plus infinity. So that gives me the distribution function. Now, of course, I could have done it the other way. I could have gotten the integral from minus to plus infinity of the distribution function of x1 evaluated at t minus u, density function of x2 evaluated at u, du. Didn't matter whether I add x1 plus x2 or x2 plus x1. Okay, so this is to do this in a rigorous fashion. The way it's done in the book is very difficult, but you can see that if you understand what probability means, you can write this kind of stuff down immediately. So this integral just represents the theorem of total probability. I'm just conditioning on the value that one of the random variable takes, multiplied then by the probability that the other one takes whatever is required so that the sum is less than or equal to t, and then I just add up over all possible values over the partition of the sample space. Now, to get the density function, I just differentiate. So when I differentiate big F, I get little f. And when I differentiate this using the rules of calculus, all that happens is the big F here, I take the differential operator, I move it inside, I'm differentiating with respect to t, there's the only t, so the only thing that happens is I wind up taking the derivative of this function right here. But by definition, the derivative of big F is little f, so when I differentiate inside the integral, the big F becomes a little f, and the same thing over here, if I differentiated that big F would become a little f. So this is my formula for the density function of a sum of independent random variables in terms of the density functions of the individual components. Now, what you have to do in order to solve the problem is you have to evaluate this integral. You have to put it in here and evaluate this. But this is no big deal. That is, this part is easy. And in fact, this part is easy. Because remember, you've already done this for the case in which, for x1 by itself being uniform. So you already know how to do it for the case in which the density function that fits in here is the density function for the uniform variable. So now I'm asking you to do it for the particular case what I just erased. So instead of having a box as these functions, now you have a triangle as these functions. So it's one step up in difficulty, and then I'm going from a linear function, a constant function to a linear function. So the actual integration is just as easy, and everything else is analogous. So now's the time to go back and look at homework 0 and understand what you did when you evaluated that integral. When you do that, you plug the answer in here, evaluate that integral, which is going to be simple, and that's the answer. And then, of course, to see whether or not you did it right, you check it against the theory. Against the simulation. And the simulation just involves knowing how to write the code using the inverse transform method that generates the values of x1 and x2. Okay, so that's homework 3. Okay, so let me summarize where we are in the course. And then, before I do that, I guess, let me ask, are there any questions about that? Because I suppose you haven't tried it yet, so if you try it, you'll have questions. But at the moment, you should see the strategy. And the only hard part is a new part, 2 new parts, one of them's hard, sort of hard. The 2 new parts are, you have a new function, this one whose density function is a triangle. So you have to use the inverse transform method to generate values in the simulation from a population that has that density function. It's straightforward, it's not a big deal, it's simple, but you have to know what to do. You already should know what to do because you've done it in homework 3. But in homework 3, I gave you 4 cases, and now this is a 5th case. So you just do the same thing here that you did in homework 3, except in homework 3, I told you how to do each one. And remember, something like this is going to be on the final exam. I'll just give you a different density function or a different distribution function and ask you to generate or write the instruction that would generate the values in the simulation. So that's new but easy. Then the second part, which is new but maybe less easy, is actually evaluating this convolution integral for this case. And the way to do it is to look and see what was done in the case in which the both of the f's were uniform, which was what you already did in homework 0. So remember, you did it. Actually, most people didn't do it, but then I did it in class in detail. So you should have that answer worked out in detail, and what you should do is go back over that and then make the same analogous argument in this case, because the only difference here is that one of the f's is different. Remember that this involves 2 f's. One of them is a uniform, and in homework 0, the other one was also uniform, and now, in this case, the other one is not uniform, but it has this triangular shape. That's the only difference. And if everything is done correctly, then of course the answers that you get by theory and simulation should be about the same, so that's your check. Okay, so let me write down what we did in the course up to this point, because now we're ready to go on to the next topic. We're done with this chapter. I'm done with this chapter. So, according to my notes, here's sort of a summary of where we are. We talked about random variables. In fact, I think that was the name of the chapter. And the page numbers I gave were 129 and 130. And then for the discrete case in particular, there's the probability mass function, PMF, and that's discussed on pages 143, 145. Of course, the rest of the book has this stuff too, but I'm just picking out the specific, zeroing on the specific formulas or points that I discussed. If you read the rest of it, if you understand it, it should be helpful. But it's probably, in many cases, more than you need. Then we discussed distribution function. And distribution function, that's the big F. And that's on pages 134 and 135. Well, remember that the author separates continuous and discrete, which I'm not doing. I think that that's makes more sense to do them in parallel rather than do them in series. So first he discusses discrete, then he discusses continuous. Then we discussed expected values. Which was E of x. And on page 150, 151, the discrete case is discussed. And page 234, the continuous case. So remember, this is a sum, that's the integral. And in fact, this is all, at least in the discrete case, this is the basis for homework 2, which just about everybody did, and almost everybody got 14 or 15 points on that. Then we discussed density function. So now we're in the continuous case. And the density function is defined on pages 218 to 220. There's some discussion there. And then we looked at some specific cases. One was the case where x is uniform between 0 and 1, in general between A and B. And this is discussed on page 247 to 249. And also homework 0. So in homework 0, you did work with the density function and distribution function for the uniform where A was 0 and B is 1, which is the standard case. And at that time, you didn't know what you were doing. You were just doing the work. But having gotten here, now you go back to homework 0 and you see that that was an example. And this came from a model. That is, this was the idea of spinning this dial, or picking a number in an interval in which all numbers are, in a sense, equally likely. Then we looked at another particular example. That was the case that we called exponential, that's called exponential, and there's a parameter lambda. In the case that we took, for example, we took lambda equal to 2. And then this is discussed in the book on page 269 to 274. And I derived this. Remember that if x is exponential, then it describes the times between events that occur at random. What's called the Poisson process. So this is important from the viewpoint of modeling. Then we discussed variance. And remember that the variance, which I'm calling V, the variance expresses the amount of randomness, in a sense, the amount of spread, how much a particular random variable bounces around its average value. And so its definition is that it's the average value or expected value of the square of the difference between its values and its average value. And there's a formula. So instead of using a definition, you can use this formula, which is derived as a theorem, which says that the variance is equal to the average of the square minus the square of the average. And this is discussed for the discrete case on page 162, discrete, and for the continuous case on page 239. Of course, it's the same formula. So this separation of 60 or 70 pages there, as I say, is this artificial separation between discrete and continuous. And then similarly, this formula holds in both cases, and a discrete case is given on page 164 and a continuous on page 240. Then we discussed the inverse transform method. So this is very important because this is what allows you to use a computer which has a random number generator to generate random variables of any particular, from any particular population. So this is the inverse transform method. And this is illustrated in homework 3 and homework 4. And in the book, this is discussed on page 476. Although, as I say, it's I think it's harder to follow in the book, but you can check it out. And on page 477, in particular, as an example of the inverse transform method, the author discusses the exponential distribution. So the log formula that I derived in class, he derives that also in the book on page 477. And then finally, convolution. And that's discussed in homework 4, and it's given in the book on page 432. Although when you look it up on page 432, you'll see that the method that led to these results is much different from what we did in class. It's much more mathematical. So in fact, on page 432, what he does is he derives this result using methods that you would learn in calculus, say in calculus 3, and then he goes from there to there. Whereas what I did was I started with this and derived this using a probability argument, not a mathematical argument, and then went from here to here by simply taking the derivative. And that's where we stand so far. Okay, so we're ready to move on to the next topic. So, any questions? Everybody happy? Okay, so assuming that everybody is happy, the next thing I want to discuss is the normal distribution. And so now I'm going to change books. Now I'm going to go to the Ross book. But some of the stuff is in both Ross and Garamani. But some of the stuff that I want to get to, just a little bit though, is only in Ross and not in Garamani. So I'm going to use, I'll refer to both books. And the Ross book, remember, is on reserve in the library. And I wouldn't recommend buying it because we're not going to use enough of it, just a few pages. So you'll see. So let me talk about normal random variables. So this stuff is going to go. So this is in the Ross book. And it's section 5.5 in Ross. Normal random variables, or normal distribution. And the very word normal means, or gives an indication that this is ordinarily the distribution that would describe a particular population. So this is really not, it's not a good choice of words, but it's one that's grown up by convention or tradition. But still, you could think of it as being the normal distribution corresponds to the normal, ordinary, everyday case. So there's sort of a model behind it. In fact, there's a very important model behind it. But for reasons that you'll see later, it would make more sense in this case for me just to define the distribution and then later worry about where it comes from. So in the book, what he does is he gives a formula. My notation is going to be a little bit different because remember, he uses x for the, which confuses the x for the independent random variable and for the independent variable, and x is the name of the random variable in question. So, let's see, I want to use the proper notation here so I'm consistent. Okay, so I'm going to write it like this. Suppose that we have a density function, and I'll say that x is normal n with parameters mu and sigma squared. So we'll get to what those things mean. This is a Greek m, and that's a Greek s, I guess, squared. Okay, so what this means is that the density function of x is given by this formula. 1 over sigma square root 2 pi e to the minus 1/2 t minus mu over sigma squared. So that looks pretty bizarre at first glance. One thing about this that's different from what we've had in the past, though, is that this is defined for all values of t, all values of the argument between minus and plus infinity. So there's a single formula that describes this population over the whole range between minus and plus infinity. And if you draw its graph, it'll look like this. Now what this thing does is, I think you can see that as t varies, the thing that affects the height of the function is the square of the difference between t and the value mu. And it's only the absolute difference, because whether this t minus mu is plus or minus a particular number, when I square it, the minus sign is irrelevant. So it's only the absolute difference that matters. So you could see that if this is the value mu, that this graph will peak when t is equal to mu. And then if you were to draw its graph, you would see it would look something like this. So it's symmetric about mu. As t moves left or right, the only thing that's going to affect the height of the graph is going to be how far you are away from mu. And the sigma is just a scale factor, and I'm not exactly sure what the 1/2 is for. It makes it work. And this factor right over here is the normalization factor. Okay, so this is what's called the normalization factor. In other words, normalization means making everything add up to 1. Because what this thing does is it defines this bell-shaped curve, and this is often referred to as a bell-shaped curve. So let me write that down. So this part defines a bell-shaped curve, and if you calculate the area under that curve, it'll turn out that that area is the reciprocal of this. So in other words, you put this thing in here to make the total area 1. So it's surprising, kind of interesting, this sigma is this parameter right here, so it's not surprising that that sigma should be in there. That, as I say, is a scale factor. We'll see more about that in a minute. And then here you have the square root of 2 pi, which is kind of weird. It turns out that very often in applied mathematics, what you get is you get things that have the values of pi and e. How can something that's applied be dependent on things like pi and e? Why should that pi be in there? I mean, pi is the ratio of the diameter to the circumference of a circle, and e is the base of the natural logarithms. And so it's strange that lots of formulas have square roots and pi's and e's and stuff like that. And so just as a side issue, there's a famous formula which is really amazing, because you might ask yourself, if I asked you, name the most fundamental quantities in mathematics that everything is built from. And so you could say, well, let's see. You have to have the 0, and you need the 1. Everybody knows you need a 1. That's what you need to count with. The fact that you need a 0 in order to make everything be more than just trivial was supposedly one of the major advances of mathematics in the history of mankind. So when the 0 was discovered, then all of a sudden you could make arithmetic. You could make it in a more theoretical sense, understand what's going on. So you need a 0, you need a 1, and then you might say, well, there's other things. There is e, there's I, and there's pi. Okay, now, e is the base of the natural logarithms. I is the square root of minus 1, whatever that means. In fact, it's called imaginary, which is indicative of the fact that when people first started using this, since it didn't make any sense to talk about the square root of minus 1 as being a number, being something useful, so they called it an imaginary number, sort of like sinful to use it. And then pi, of course, is the ratio of the circumference of the diameter of a circle. So I might say to you, here are some of the 5 basic things that appear in lots of applied mathematics, lots of physical formulas. Can you give me a formula that's going to link all of these things together as simply as possible? And maybe you've seen this formula. Let me write it down. E to the I pi plus 1 equals 0. How many people have seen that formula? Anybody? It's easy to prove, at least in a formal sense. So this says that if you take the base of the natural logarithms and you raise it to a power that has in it the square root of minus 1, which is an imaginary number, and pi, this ratio between the circumference and diameter of a circle, and then you take the simplest operation, which is adding, and you add to it the basic element 1, the result will be equal to, this is again a very fundamental symbol, meaning left side equals right side, equals 0, and these 5 things are all linked together in one simple formula. So it's easy to prove this, but it's kind of mysterious. So I always say that anybody who can explain this, the secret of life is in it, secret of the universe. Because if you think about it, all facts that are true, especially mathematical facts that correspond to logic, they have to be true. How could you imagine a universe in which any particular fact that we accept as true is not true? Like if it turned out that pi was some other number, what would the world look like? It's inconceivable. Circles would be different. Everything would be different. Maybe gravity would be reversed and we'd all be flying up against the ceiling. It would be very hard to see the board. So these things, the fact that this simple thing works to me is amazing. So as I say, it's easy to prove, but if anybody can explain why it is, as I say, the secret of the universe is in here, then you can get an A. So anybody can explain the secret of the universe gets an A in the course. So far, people have gotten A in the course. It's not that hard, but nobody has gotten it by explaining the secret of the universe. So that's your challenge. Okay, anyhow, forget about all this. It has nothing to do with the course. This bell-shaped curve is a picture of this density function, which is called the normal density function. And the basic idea is you got this population, and the population has random values in it, and there's some mid-value, which we're calling mu, and then there's a bell-shaped curve that describes the densities about mu. So the farther away you get from mu, the less and less, the smaller and smaller the density function gets, and it's symmetrical. So you can see that this is sort of the idea that you would expect if you take data, that the values would tend to cluster here, and then the farther away you get from the central value, the less likely it is that you will get that value, and it doesn't matter whether you're talking about deviation in this direction or deviation in that direction. So if you were trying to think up sort of a general description of a random population, you would probably come up with some kind of idea that you should have sort of a bell-shaped curve. Okay, so this formula gives a bell-shaped curve, and this just makes the area under that curve be equal. And in mathematics books, and in fact in our book, they make a big deal over proving that the area is 1, but all of that stuff is irrelevant. Okay, now suppose I calculated the expected value of this random variable. Well, by definition, this would be the integral from minus plus infinity of t, the values the random variable takes, times its density function. 1 over sigma square root 2 pi e to the minus 1/2 t minus mu divided by sigma squared dt. Okay, so that would be the expected value. And if you evaluate that integral, of course the answer will turn out to be mu. Because, after all, it's not surprising if the picture of this density function, if its graph is a curve that has a symmetry, then obviously the average value is going to be that value right in the middle. So if you do this arithmetic, which again is a lot of arithmetic, but is not really important from our point of view, so I'll say after much calculus, after much work, you get the value mu. So the mu, the parameter that fits in here, is the value, the central location. It's the expected value, the mean value. What's the variance of x? Well, the variance of x, formally, would be given by taking the values the random variable takes, and you take the, let me say that again. The variance, remember, is the average value of the square of the difference between the values the random variable takes and its average value. So this is the expected value of t, that's the values the random variable takes, minus its expected value. You square that, and you weight that by the density function. So that would be 1 over sigma square root 2 pi e to the minus 1/2 t minus mu over sigma squared dt. Now you evaluate that integral. Of course, it's a mess, but after much work, it will turn out that the answer is sigma squared. So this parameter right here, sigma, that guy there, which is a scale factor, is in fact the square root of the variance. So sigma squared is the variance, and sigma, which is therefore the square root of the variance, that's called the standard deviation. So for any given value of mu, I have a family of these curves, because the standard deviation, which is the square root of the variance, is a measure of how much spread there is. So if the standard deviation is large, that means that the population values spread out, and the curve would look like this. So as the variance gets larger, the curve gets flatter, because remember, the total area always has to be 1. And as the variance is smaller, the curve looks more like that. So you've got this collection, this family of these curves. Now, if you take a course in statistics in a business program or an education program or something like that, where calculus is not required, it turns out that this is very important material for applications. And I'll get into that shortly. But in order to be able to understand this, at least at the level we're talking about, you have to know calculus. But for most of these applications, areas like education and business, then calculus is really not required. And in fact, if you make people take calculus before they can study these other application areas, then it becomes very difficult, because then people don't take it, or you have to give a watered-down version. So the result is that any course you would take that does not require calculus and probability often starts off with the normal distribution, but it doesn't really explain what's going on. They give you a formula, and they give you tables for looking this up, and then they have to convince you as to why it is that real populations are in fact described by this bell-shaped curve. Okay, so first, recognize, let me state that if I want to find the probability that a random variable value drawn from a normal population lies in any particular region, I have to evaluate the integral of this thing in that region. That is, if I want to find out the probability that x lies between a and b, it would be the integral of this, the area under this curve, between a and b. But you can't actually evaluate that area because I shouldn't say you can't do it, but it's difficult, because the integral of this is not evaluatable, cannot be evaluated in terms of elementary functions. In other words, there is no elementary function in terms of logs, sines, cosines, things like that, whose derivative is that. So that means that even though in principle this is easy to do because it's just an area, in practice you can't do it using ordinary calculus. Okay, so let's go back here. So if I have this curve, okay, so there's the value mu, and I want to calculate the probability that x lies between a and b, then that would be this area, say. If that's a and that's b, then it would be that area. But since I can't evaluate that area by calculus, that means that I have to do something else. So one thing I could do is I could make tables which have these areas worked out. But I'd have to have an infinite number of tables then to make this useful. Because remember that every normal population has two parameters. It has a mu and it has a sigma. And so for every mu and sigma, there's going to be a different curve, and therefore there's going to be a different table, so this would not be very useful. But it turns out that there's a way to handle this problem, and that is that I can look at what's called the standard normal variable. Okay, so what I'm going to do is I'm going to let z equal x minus mu divided by sigma. And So I'm going to come up with a rule by which if you give me tell me that a population is normally distributed, and you tell me it's mu and it's sigma, then I can change this to a question about another random variable z called the standard normal variable. Remember, anybody can do this now. Education majors do this, business majors. You don't have to know what you're doing. But I'm going to explain why this works. So what you do is you perform this transformation, and then you change the question about x to a question about z. And then you look up z. You only need one table. That's the standard normal table that's in every book. So I don't need an infinite number of tables. I need a single table. And so let me do that. Okay, so suppose that I know that x is normal with parameters mu and sigma, or sigma squared. When people write it like this, sometimes I write sigma, sometimes I write sigma squared. You got to know which one you mean. So I'll always write the square in there. Okay, so I have a certain mean and a certain variance. The square root of that variance is what's called the standard deviation. And what I want to do is I want to define a new random variable z, which is the original one with the mean subtracted and the standard deviation divided out, the scale change. So I want to find the distribution function of z. So in other words, that's the probability that z is less than or equal to t. But that's the probability that x minus mu over sigma is less than or equal to t. But that's the probability that x is less than or equal to sigma times t plus mu. But that, if x is normal with mean, mu, and variance sigma squared, would be equal to the integral from minus infinity to sigma t plus mu. Because I want less than that. So it's the integral from minus infinity to sigma t plus mu of the density function, which is 1 over sigma square root 2 pi e to the minus 1/2. Let's see, I have to change the variable here, so I'm going to call it y. So it would be y minus mu over sigma squared dy. Okay, so this right here that I wrote right there, that's the density function of the random variable x, the normal, and I'm calling the independent variable y because I've already used the t for here. That's the t that's right there. So now I want to evaluate this integral. So to evaluate this integral, of course, what I'm going to do is I'm going to make a substitution. So I'm going to take the y minus mu over sigma. So right here, I'm going to say y minus mu over sigma. I'll set that equal to little x. So when I do that, this becomes the integral of 1 over sigma square root 2 pi e to the minus 1/2 x squared. Okay, y minus mu over sigma is x. So that squared becomes x squared. And now what about the rest of it? Well, I have dy. So I can see here that y is equal to sigma x plus mu. So dy is equal to sigma dx. Remember, mu is a constant. So this is the same old stuff that we did earlier, in which you evaluate an integral by making a change of variable. So that means that I replace dy by sigma dx. Now what about the limits? Well, when y is equal to infinity, then x is minus infinity, then x is equal to minus infinity. So that limit stays the same. Now go back over here and set y equal to sigma t plus mu. So if I replace this y here by sigma t plus mu, the mu cancels, then the sigma cancels, and I'm simply left with t. So that puts a t here. And then I recognize that the sigma cancels out. So what I'm left with is the distribution function of z is the integral from minus infinity to t of this thing right here. But if you look back at the definition of the density function of a normal random variable, you will see that this is the same as this, except I've replaced t by x, same density function, if mu were 0 and sigma were 1. So this thing corresponds to a normal variable whose parameters are 0 and 1. So what that means, and I'll illustrate this, is that if I want to evaluate the probabilities associated with a random variable that's normal with a mean of mu and a variance of sigma squared, what I can do is I can change the variable. I can say, okay, instead of worrying about x, I'm going to worry about z, which is the difference between x and its mean in units of its standard deviation. So I make this transformation. I'll show you how to do that in a minute. I just did it here. And when I get done, I find out that the new random variable z, which is a function of the old random variable x, it in fact has a distribution function that is exactly the same as the distribution function of a random variable that is normal with mean 0 and variance 1. So in other words, if z is equal to this, then z is normal 0, 1. So this is a theorem. Okay, so let me write it down and then give you the reference in the book. Theorem. If x is normal with parameters mu and sigma squared, then z, let's say this, then z, defined as x minus mu over sigma, is distributed as a normal with mean 0 and variance 1. So, x has that distribution, z has that distribution. Now I can always change my x into a z, which means that I can always transform a question about a random variable with these parameters to these parameters, which means I need only one table. So I have the table for this, which is called the standard normal variable. So z is called the standard normal variable. Now, as I say, if you had taken a statistics course in an applied area like education, business psychology, things like that, social sciences, usually this is where you start. Now, how many people have seen this before? Anybody? Okay, 2. But it's true, right? I mean, I didn't make this up. This is standard stuff. Okay, so let me see where this is in the book. In Ross, this is on page 162. And in Garamani, it's on page 261. And the notation is pretty much the same. Now, in the particular case of the standard normal variable, then the density function is given by, let's say that this. For the standard normal variable, the density function is called little phi. So this is just the name that you would use. That little phi then means it's 1 over square root 2 pi e to the minus 1/2 t squared, or t lying between minus infinity, I don't want this equal sign here, and plus infinity. And the distribution function of x, so I should really say z, because I'm talking about the standard normal. Okay, so if the standard normal variable is called z, its density function is called little phi, that's a Greek f, I guess, and its distribution function is called uppercase phi. And that would be the integral from minus infinity to t of lowercase phi of, let's say, x dx. So this is the standard notation for the density function or distribution function of a normal random variable that's in the standard form. That means its mean is 0 and its variance is 1. Okay, so now let's look at the table. So at the moment, this is kind of, I don't know, boring, because all I'm doing is defining something, telling you some properties, and it's not clear why anybody cares. But lots of things have this bell-shaped curve. Okay, so there's the mu, there's the curve, and what you do is you take one for any particular mu and sigma, and you change it by this to make it one where the mu is 0, the sigma is 1. So that allows you to use the table, but in the original form, what I'm implying here is that lots of real populations are described by bell-shaped curves that look like this. And in fact, almost anything you could think of. A good example is IQ scores. So I'll talk about that because that's one that people are interested in. IQ scores tend to be normally distributed with a mean or mu of 100. In other words, 100 is the average IQ score, and there's a standard deviation, which I think is 15 points. So that means that if you know someone's IQ score, then you could calculate where it falls on this curve. In other words, it's the same thing. Telling you someone's IQ score is this, or telling you that IQ scores are normal with a mean of 100 and a variance of 15, standard deviation of 15, will then allow you to calculate, for example, the fraction of IQ scores that lie between, say, 120 and 128 or whatever you want. So why are IQ scores normally distributed? Why is anything normally distributed? Well, we'll get to that shortly. One reason is what's called the central limit theorem, which is one of the major results of probability and statistics. So that's why I'm sort of doing this backwards. First, I have to say what we have here, and then I have to go back and show that this particular formula, which at first glance looks like it's kind of strange, in fact describes almost everything. If something isn't uniform or exponential, to be flip about it, it's probably normal. Okay, so here's the table, and this table is on page, in Ross, it's on page 570, and in Garamani, it's on page 488. And every statistics book, or probability and statistics book, has this in it. Okay, so this is the way it appears in Ross's book on page 570. He calls it, he says it's the standard normal distribution function, phi of x, and then he writes down the formula. 1 over square root 2 pi, takes that outside the integral. Integral from minus infinity to x, e to the minus y squared over 2 dy. So this is what he's going to tabulate. In other words, it's the area under the standard normal density function to the left of x. Okay, so here's the standard normal density function. Its mean is 0. It looks like that. Here's the value x. Capital phi of x is that area. And what's in the table is you look up the x and it tells you the area. Okay, so it looks like this. Let's see. here's the value of x. Running out of space here. I'll do it like this. Here's x. And here is 0.00, 0.01, 0.02, and so forth, 0.09. And then running down here, he has the value 0.0, 0.1, 0.2, 0.3, and so forth. And it ends up at 3.4. And then he has the values. For example, this value is 0.5000. Obviously, the area to the left of 0.000 right there is half the area, because the total area is 1. Half the area is therefore 0.5. The area to the left of 0.01 is 0.5040. And the next entry is 0.5080. And over here it's 0.5359. And this entry right here is 0.5398. And this entry is 0.5793. And so on. And this entry down here is 0.9997. And here it's 0.9998. Okay, so this table is in all the books. And the idea now is that if you tell me that you have a random variable that's normally distributed, and you tell me the mu, and you tell me the sigma, tell me the mu and tell me the sigma, then if you ask me the probability that that random variable lies in any range, whatever you ask me for, I can change that by performing this transformation, plugging into this formula. I can change that to a statement about z, and then I look up the answer to the statement about z in this single table which is in every book. So in other words, you got one table that describes the world. So let's do some examples. Let's see, before I do that, there's one more thing I want to tell you. If you look at this table, you'll notice that this works only for values of x that are not negative. In other words, it starts here, and the values in the table in x are all values. These values in here are all greater than 1/2. In other words, it assumes that x is negative. So what do I do about that? Suppose I want to get a negative value. Assumes that x is positive. So you can draw this picture. You don't need to prove it. Here's x. So here is minus x. This is 0. If I want to find the area to the left of minus x, that is capital Phi of minus x. It's not in the table, but you can see that the area to the left of minus x is the same as the area to the right of plus x, because this curve is symmetric about 0. Now, what's the area to the right of plus x? That's 1 minus the area to the left of plus x. What's the area to the left of plus x? Phi of x. So here we have 1 minus capital Phi of x. Okay, so this formula is in the book. Let's see, this is in page 163 in Ross, and it's page 256, Garamani. Okay, so you can see it's simple enough. The area to the left of minus x, which is by definition capital Phi, is equal to the area to the right of plus x by symmetry. Now, the area to the right of plus x is 1 minus the area to the left of plus x, and the area to the left of plus x by definition is capital Phi, which is what's in the table. So therefore, even though the table only gives me values for x that are not negative, I can get values for all x. In fact, if you wanted to write the table for all x, you just take the same table and copy it. I mean, it's just to waste paper. Okay, so let's do some examples now. So everybody okay, or anybody have any questions on this? Let me summarize. All I said was that lots of random variables are described by a bell-shaped curve. There's two parameters that describe it. The mu tells you where its center is. The sigma tells you how spread out it is. Since lots of variables are described by this, you would want to be able to evaluate the area under this curve. However, the area under that curve, being an integral, it turns out is difficult to evaluate by ordinary calculus because the formula for that curve has got this exponential with a square in it, and there is no simple formula whose derivative is that. So therefore, I can't easily use the fundamental theorem of calculus to evaluate these areas. However, I can get around that by the following trick. What I do is I define another random variable, conventionally called z, or the standard normal variable, which is the original with the mean subtracted off and the result scaled or divided by the standard deviation. When I do that, what I proved by taking this change of variable in the formula, if I do that, then the z that I get, the new random variable, will have as its density function, the density function for a random variable that is normal with parameters 0, mean 0, and variance 1. Okay, so this then becomes this. In other words, by making this transformation, I just move the curve over and rescale it so that it's a standard shape. And then any question I had about x is changed to a corresponding question about z. And since z is normal 0, 1, that means that I need only one table that has these areas in it, namely the one for mean 0 and variance 1. That's the table that's in all the books. So now, any question I want to answer about any random variable that I know is normal with any given mean and any given variance, I change to a question that I can answer by looking things up in this table. Okay, so let's look at such a question. Again, you have to take my word for it that I care about these things. But what I plan to show you soon is that of course I care because almost everything has this distribution. Okay, so here is example 5.5a in Ross on page 163. So what he says is, suppose x is normal and its parameters are mean 3 and variance sigma squared equals 16. Okay, so I'm writing it out that way so it's as clear as possible, because if I just wrote the 16, you might not be sure whether 16 was the variance or 16 was the standard deviation, which is the square root of the variance. So since I'm telling you that the variance is 16, I'm telling you that the standard deviation is 4. And of course, something about problems in textbooks is the variance is always a perfect square, so you can figure out the standard deviation without having to do arithmetic. Now the question is this, question A. He says find the probability that x is less than 11. Okay, so how do you do that? Remember, standard normal variable is x minus mu over sigma. So I changed this to a question about z. So instead of using x, I'm going to write the probability that x minus mu, which is 3, divided by sigma, which is the square root of 16, is 4, is less than 11 minus 3 divided by 4. So what is that? This is then the probability that z is less than or equal to this. Or less than that. Well, the less than or equal to, the equal part doesn't matter, because remember we're talking about a continuous random variable, and I've said 1,000 times, the probability that a continuous random variable takes any specific value is 0. So this is the probability that z is less than 11 minus 3 over 4, which is 2. 8 over 4 is 2. What is that? Well, that's capital Phi of 2 by definition. Capital Phi is the distribution function for the standard normal variable. What's capital Phi of 2? So now I go over here to my table, and I have to look up the entry in the table that corresponds to 2. Well, if you go to the table, you go down here, and you find out that here's the value 2 right there, and it would be 2.00. So it would be the entry that's right here, which is 0.9772. So the answer is 0.9772. Okay, so the actual implementation of this question is so simple as to be ridiculous. So you could take any person and say, okay, first of all, for all practical purposes, everything is normal. Then you say, if I want to find the probability that a normal variable is less than a certain number, I have to tell you two parameters. I have to tell you what its mean is and what its variance is. Okay, so I give you those two numbers. How you get those numbers in reality, that's a different question. We're starting at the beginning. So I have these two numbers, the mean and the variance. I ask the question, what do? I just take this value here, I subtract the mean, I divide by the square root of the variance of the standard deviation. Of course, in a textbook, it always comes out to be something simple. And now I go to the one table for the standard normal variable, and I look up the entry in the table for that value. So I go over here to this table, there's the 2, there's the value, 0.9772. So you don't have to know anything in order to be able to answer the question. So that's good and it's bad. It's good because it's really easy, anybody can do it. It's bad because it's really easy, anybody can do it. Right? This is important. So you don't want people making important decisions by looking things up in tables that they have no idea where the tables came from. And my view is that the reason the world is in such sorry shape that it is because public policy is made by people who are basing their decisions, basing their methods on the standard normal distribution, which they have no idea what it's about. Half the time they look in the wrong table. So that explains a lot about life. Okay, so I'm going to continue with this. That is, I'll do a couple more of these examples next time. They're all straightforward and simple. And then the big deal is to show why the normal distribution describes almost everything. And the answer to that is what's called the central limit theorem. And the central limit theorem says, in effect, that average values are normally distributed no matter what population they come from. So this is truly amazing. Because remember, an average value is a sum of values divided by the number of terms in the sum. So if you compute an average value, no matter what the population is that produced the values that added up to make the sum, the average is just as if it came from a population that is described by this one table. That's the central limit theorem. And we'll test that. We'll show that that's true by actually simulating, by picking values from different populations. And of course, what's an average? Well, it's a convolution. So this is going to make everything then tie together, but you don't have to understand any of this to simply go to a particular table and put things up. Okay, so we'll start with that next time. Any questions before we quit? We've still got a minute's worth of questions. Okay, see you in a week. Have a good